Okay, students, so the last time we discussed that damped oscillation has a general solution like this. Now there are three cases that we are going to deal with. Case 1 is called the underdamped motion. Underdamped, when this value of B, remember this B was damping constant. See, it was directly related to gamma, which was the damping force, which was related to the damping force. So if B is more, means that the damping is high, and if B is small, then it means that the damping is low. So the underdamped, the name suggests, B would be, let's say it is lesser than omega naught. That is the natural frequency of oscillation. So if B is less than this omega naught, then this term B square minus omega naught square is going to be a negative number, because this is B square would be less than omega naught square. So I can write B square minus omega naught square as minus of omega naught square minus B square. So omega naught square minus B square would be a positive number since omega is greater than B. So putting this in this, we have root of B square minus omega naught square is minus of omega naught square minus B square, and this minus 1, square root of minus 1 is the imaginary I. So you have I of root omega naught square minus B square. So if B is less than omega naught, I can replace this B square minus omega naught square by I of root omega naught square minus B square. So everything is there, A into I, e to the power of I, root of omega naught square minus B square, t, and plus B into e to the power of minus is there, so I comes out, omega naught square minus B square t. So whenever you have e to the power of I something, this becomes oscillatory in nature. Since you know e to the power of I theta can be written in terms of cos theta and sin theta. So e to the power of I something is always oscillatory in nature. So I can write this as e to the power of minus of bt is out, it is a constant factor, a e I omega t plus b e minus I omega t, where omega square is this, omega naught square minus b square. So if you square root it, you would get an omega. So e to the power of I omega t can always be written as cos omega t and sin omega t. Again, this can be written in terms of cos omega t minus sin omega t. So these are all cos and sin terms. So this is oscillatory in nature. So you can see that this solution is oscillatory in nature. So this oscillates. But this does not have an I factor. This is exponential term, and it is exponentially decreasing with time. You can see. So this is the amplitude term, and this is the oscillatory term. So in other words, this is the solution. So you can say x e to the power of minus of bt is common. So I can write e to the power of I omega t as cos omega t plus I sin omega t plus b. This was e to the power of minus I omega t. So I have written it as b cos omega t minus I sin omega t. So I can take the cos omega t as common, cos omega t common. So it becomes a plus b. So it becomes a plus b, and I is there. So a minus b will be there in case of sin omega t. This is the mathematics. You can do it on your own. So this is what you have. So I can put a plus b as a constant, c, and I a minus b as d. So this again two unknown constants, c and d. But here you can see that this is oscillatory in nature, the solution, and this is exponentially decaying in nature. So what will the solution x look like? The solution x would look like, this is oscillatory. This represents, oscillation represents this function, and you can see that the amplitude is reducing. This is the amplitude part. This is reducing. If you did not have this, then you had this term. This would have a fixed amplitude. But this case, the amplitude is decreasing with time. The amplitude is exponentially decreasing with time. So if you compare it with free oscillation, you had xt as this. You can see the amplitude remains fixed in that case. That was the free motion. And in case of damped oscillation, underdamped oscillation, you still have an oscillation, but that oscillation, the amplitude of that oscillation decreases with time. So physically speaking, if you had a free oscillation and if you have a mass, if I pull that mass, there is no friction. Let us suppose it is in the outer atmosphere. Let us say it is in space, outer space, so no drag force is there, nothing is there to drag. So if I pull this and if I release this, then this mass will oscillate freely, and this is an oscillatory motion. So this one, the oscillatory motion, so this will execute a to and fro motion, and its amplitude is going to remain fixed. So every time it is going to go up to this, come back over here and go again up to this. So the amplitude, the maximum displacement, will be fixed in case of free, because the energy is conserved, if you remember. So it will keep on oscillating forever. If you leave this oscillator in free space, in outer space, it will keep on oscillating forever, because there is no decay of energy, there is no damping. The total mechanical energy will always be conserved. But if this system is kept in air, let us say this is in air, so air will have a drag force on this. The drag force that I was talking about, the air will have a drag force on this. So now if you release this mass, then this mass will definitely oscillate if the drag is not much. That is underdamped. If the viscous force is not that big. For air, we know the viscous force is not that big. So this mass will oscillate, but this oscillation will decay with time. So if I release it from this, it will surely oscillate, but every time it comes back, it won't come back to its initial amplitude. Every time after oscillation, its amplitude will reduce and finally it will come to rest. So if you release, for example, a pendulum in free space, that pendulum is going to oscillate forever in free space. But if you release a pendulum in air, then its amplitude will gradually decrease and it will become zero. So that is underdamped motion, and that is what is shown in this graph. It is oscillating because the damping is not large. It will oscillate, but every time it comes back, it does not come back to its original amplitude. See, the original amplitude is this. So in the next part, it comes over here, not over here. Again it oscillates, it comes over here, not here. So every time its amplitude, its maximum displacement decreases than the previous one, because it is damped. The drag of the air is damping this oscillation, and finally the energy of this oscillator dissipates as heat into the environment. So there is a dissipative force. So damping force is dissipative in nature. It dissipates the energy of this oscillation into heat into the atmosphere. So free oscillation, it will always come back to its original position. Again, the amplitude is fixed, so it will oscillate like this forever. Nothing is going to decrease its energy because nothing is there. But if you oscillate this in an environment which has a drag force, then this amplitude will reduce every time and it will come to rest finally. So its mechanical energy now is not conserved, it is being reduced, and that energy goes away as heat. Right? So the graph looks like this. So it is underdamped, it is going to oscillate, but every time it oscillates, the amplitude is going to reduce, and the reduction of amplitude is given by this term. So this is the damping term, and the oscillation is going to be in this mathematical entity. This represents oscillation, and this will represent decay of amplitude. And please check, the decay will depend upon B, the value of B. B, you know, is related to the damping, or it is the damping constant. If the damping is large, then it will reduce quickly. Or if the damping is large, huge amount of damping is there. Huge amount of damping is there. Right? And one more thing, the free oscillator was oscillating at omega naught. But this oscillator, the damped oscillator, is oscillating at omega frequency. You can see. And omega is not equal to omega naught. Omega is equal to square root of omega naught square minus B square. So omega is different than omega naught. So two things are different in case of free and damped oscillation. This is free oscillation and this is damped oscillation. So one thing is the amplitude remains free for the amplitude remains the same for free oscillation. In damped oscillation, the amplitude will exponentially decrease, and the free oscillation was happening at a frequency of omega naught, whereas the underdamped oscillation is taking place at a frequency omega, which is different from omega naught. So these are the basic differences. So this was underdamped motion. Now let us study case 2, which is overdamped motion. As the name suggests, overdamped, the damping is going to be very much high. That is, B is going to be greater than omega naught. If B is greater than omega naught, if you look at this equation, if B is greater than omega naught, then this is going to be a positive quantity. This is going to be a positive quantity. So definitely no need to put an iota sign, or I, imaginary number will not come. But look at this. This is a positive quantity. This is a positive quantity, and this will grow with time. This is positive number. So as time increases, this number will also increase in time, so that x will increase in time. So this is not a physically possible solution. You cannot have the displacement increasing with time. So mathematically, though mathematically this is a possible solution, but physically this is not a possible solution. But this is, because again this is positive, but there is a negative term. So this is exponentially decaying with time. So this is a possible solution. So we'll take this as mathematical possible solution. So I'll put root over B square minus omega square, root over B square minus omega naught square as, let us say, alpha. So you have B, only this term will survive, only this term will survive, because this is physically not possible. This will grow with time. E to the power of minus bt is there. So you have only the B constant, e to the power of minus bt, and e to the power of minus alpha t, where alpha is this, root over B square minus omega naught square. So you have this. So you see, you have B e to the power of minus B plus alpha t, where alpha is this. So you can see here you have no oscillatory term. This is exponentially decreasing, no I factor. You cannot break this to cos and sine terms. So this is exponentially decreasing. So if I plot x versus time, it will be exponentially decreasing, this factor. This would be exponentially decreasing. So no oscillation is there. So if you have a very, very high damping system, a system which has a very high damping value B, then the system will not oscillate, but it will slowly come to x equal to 0, that is the mean position. So in other words, try to understand, if this liquid has a viscosity, kind of a small viscosity, then this mass will oscillate, but the oscillations will finally reduce to 0, but it will have an oscillation. But if the viscosity of the liquid is very high, let us say you put the spring mass system in a jelly. A jelly is a very, very thick liquid. So if you put it inside a jelly and if you release this mass will not oscillate at all. It is an overdamped system. This mass will, if you stretch this mass and if you release it, this mass will slowly come to the equilibrium position. It will not overshoot and oscillate. So this is called overdamped motion, because the damping here, the system over here, that is the liquid, is very, very thick, and it will not let this mass overshoot its mean position, and it will slowly come to the equilibrium position, and it will not overshoot. So this is what the graph shows. This is the mathematical form of it. This will slowly come to the equilibrium position as time increases, but there is no oscillation. You can see there is no oscillation. The displacement reduces to 0 at, let us say, time infinity, but it will slowly reduce to 0. So this is overdamped motion. Now in between overdamped and underdamped, so please understand, underdamped you are going to have an oscillation, but the amplitude will gradually decrease. In overdamped, since the damping is very high, you will not have any oscillation, and the displacement will slowly decrease to 0. It will not overshoot the mean position. For underdamped, it will overshoot the mean position because it is not very much damped, but the amplitude is gradually going to decrease, and finally it will come to 0. But for overdamped, since the damping is very high, it will slowly come to the equilibrium position and will not overshoot. So this is what we have. But in between these two, that is underdamped, and overdamped, we have another situation which is critically damped. In critically damped situation, we have taken b less than 0 for underdamped and b less than omega naught for underdamped and b greater than omega naught for overdamped. In critically damped, b is more or less equal to omega naught. So let's see what happens if b is very much nearer to omega naught. Let's say these two are very much equal. So let us put b square minus omega naught square, this term, let us put b square minus omega naught square as h square, where h is a very, very small number. Since b and omega naught are very much same, they differ by a very small amount. Let's say the difference is h square, and this h square is very, very small. So we can write this as b square minus omega naught square as h square, and if you take the square root, you will have h. So the solution is e to the power of minus bt is common, a e h t plus b e minus of h t, a e h t plus b e minus of h t. This is what we have. Now we know that e to the power of ht can be approximately written as 1 plus ht plus the higher powers of h square, h cube and all. But if h is very, very small, as we considered, then we can neglect the higher order terms. So e to the power of ht can be approximately written as 1 plus ht. E to the power of minus ht can be similarly approximated as 1 minus of ht. So let us put these approximations in these. So we have e to the power of minus bt, e to the power of ht can be approximated as 1 plus ht, plus e to the power of minus ht is 1 minus ht. So I take a plus b, here you have a plus b, and you have aht minus bht, so you have a minus b ht. Again, this is a constant and this is a constant, so I can replace this by c, and this a minus b h by d. So I have e to the power of minus of bt, c plus dt. So this is the solution for critically damped oscillation. So where is this different? Again, this is not oscillatory in nature. Again, the critically damped motion is not oscillatory in nature. So this is exponentially decaying. Definitely. Again, the mass does not oscillate. But what is the difference try to understand the difference between critically damped and overdamped. Even in case of overdamped, you did not have any oscillation. Even for critically damped, you are not having an oscillation. It is exponentially decreasing, the x value. Then what is the difference? See, the name suggests critically damped. If B is very much greater than omega naught, or B is greater than omega naught, that is overdamped, it is not going to oscillate. And if B is less than omega naught, it is going to oscillate, underdamped. But if B approaches omega naught, that is the least value of B for which no oscillation takes place. So basically, if B is greater than omega naught, definitely there will be no oscillation, overdamped. If B is less than omega naught, then again there will be oscillation, but the amplitude will reduce. But if B is more or less equal to omega naught, then it is just that value of B for which oscillation will cease to exist. There will be no oscillation. After this value, definitely there won't be any oscillation. That is, if B increases, there won't be any oscillation. But this is the critical value of B which separates the overdamped and the underdamped motion. So basically, this is the value of B. This is critically damped motion, is where the mass will come to the equilibrium position fastest. See, if this liquid has a very low damping value, if this liquid has a low damping value, then this is going to oscillate. And if this liquid has a very high damping value, then this will slowly come to the equilibrium position. Now, if the liquid has a critical damping value, that is B is equal to omega naught, then this will come to the equilibrium position, will not shoot, but this coming of this mass to the equilibrium position will be fastest. Because if I increase the damping, then damping is so huge that this mass will very slowly approach the equilibrium position, because the damping is very large. If the mass wants to move in this direction, but the damping is so huge that it is going to make the mass move very slowly. But if the damping is not so huge, then this will move quicker than the previous case. But if the damping is sufficient enough to not let the mass overshoot this equilibrium position, then that is the critically damped case. Then this mass, that means this mass will come to the equilibrium position and will not overshoot for critically damped case. But this happens in the least amount of time. This happens fastest for critically damped motion. For overdamped motion, this comes to the equilibrium position, but this takes time, much more time than the critically damped case, because the damping is large. It will make the mass move towards this direction very slowly. But critically damped motion, this will make the mass move towards this at a faster rate, basically the fastest rate. And but the damping is such that it will not let the mass overshoot this equilibrium position. So it is not oscillatory in nature, but it reaches the equilibrium position in the smallest or the lowest amount of time. It reaches the equilibrium position fastest. So critically damped motion is that the mass will not oscillate. It will stop at the equilibrium position, but it will reach the equilibrium position fastest. So try to visualize this. If this is a pendulum, and if it oscillates, see what are the various conditions. If this is a free oscillation, then this pendulum will oscillate freely, and its amplitude will not going to decrease. It will remain the same. So the pendulum is oscillating freely. You can see the pendulum is oscillating freely and the amplitude is also fixed. If it is underdamped, then there will be oscillation, but the oscillation will reduce with time. So this and like this, and it will come to 0. This is underdamped. For overdamped, if I release this pendulum from here, and here you have a viscous liquid, then this pendulum will very slowly come to the equilibrium position. See, there is no oscillation. It is not overshooting. Underdamped, the damping was low, it was overshooting, but it was slowly reducing to 0. In overdamped, it slowly reaches, because the damping is so huge, it slowly reaches the equilibrium position and stays. So no oscillation. In critically damped, again there is no oscillation, but it reaches the equilibrium position very fast, the fastest. Again, it does not overshoot. There is no oscillation. But here, overdamped, it was very, very, very slow. Very, 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 very slow to reach the equilibrium position, because the damping was huge. It is not letting the pendulum reach the equilibrium position. In critically damped, there is no overshoot, there is no oscillation, but it will reach the equilibrium position fast. So if you graph it, I have graphed it, all the three. This is underdamped. You can see oscillation is there, but the amplitude is reducing. So 1 is underdamped. I have marked it. 1 is underdamped. 2 is overdamped. 2 is overdamped. You can see exponentially decreasing, but it will take huge amount of time for x to reduce to 0. So it will take a huge amount of time. If I extrapolate this graph, it will take a huge amount of time. So time will be very huge when x becomes 0. 3 is critically damped, this dashed line. You see, again it is non-oscillatory, but it is reaching the 0 point, that is the equilibrium point, very fast. 3. So 3 is critically damped. 2 is overdamped. It is taking too much time to reach. This graph will take too much time to reach 0, baseline. Whereas 3, again non-oscillatory, but it is coming very fast to this baseline. So 3 is critically damped, 2 is overdamped, 1 is underdamped. There is oscillation. So thank you. These were the 3 types of damped oscillatory motion. In the next class, we'll be dealing with forced vibration. Thank you.